Hi, my name is Abhilash Majumdar. I am a research scientist from Morgan Stanley. Previously, I used to work for HSBC Holdings as a machine learning NLP engineer. And I have also worked with Google Research for the language models and have contributed and maintained BERT and Albert. Before that, I have been mentoring students and professionals from different organizations like Udacity, Udemy, Upgrad on different machine learning projects, natural language processing. Um, in general, so I have been working in this mentorship area for quite a long time, and you can find the links to connect with me in the description given below. So welcome to the Core Learning Lounge YouTube channel. Today I will be explaining you the word embeddings from Jay Alammar's blog post, the illustrated word embedding, the illustrated word2vec. Also make sure to subscribe to this YouTube channel because we're going to explain all the important concepts of NLP in a series of videos. In the next video, we're going to cover about different topics like attention, transformers, BERT. So let's get started with the illustrated word2vec. So in this post, we're going to cover the concept of word2vec, how it was created, what are the different aspects of it. In general, when we talk about embeddings, it is a very fascinating idea because all the language models that we see today rely on embeddings. Embeddings naturally give meaning to the words that are currently used, and there have been several advancements in this context to recent developments like BERT, GPT-2, transformer-based models. But the base of all these models comes from word2vec, which is one of the oldest, and it has been around 2013 since 2013, and most of the big organizations like Alibaba, Spotify, they still use them. And we're going to talk about how word2vec embeddings are generated and how they are created by different logics like skipgram and common bag of words in this current blog written by Jay Alammar. So the first thing, how we can what do we mean by embeddings? So let's say, suppose here Jay has given an example that about a personality, right? What are the different characteristics of a particular personality? So it can have agreeableness, consensuousness, negative emotionality, extraversion. So let's say we take into consideration only introversion and extraversion. So, and let's say, for instance, we have an introversion score of 38 out of 100. So when we plot this into a scale, we can see that 38 will be placed somewhere between 0 and 100. Now, if we normalize that score over here from -1 to 1, we can see that that gets translated to a probability value of minus zero point 0.4, equivalent probability value of minus zero point 0.4. Now, if we were to find another person who is similar to me, having the same kind of introversion score, then we need this particular score, right? Because other than that, how were we able to identify someone else with almost similar characteristics? So in this case, we have only one characteristics, that is the extraversion or the introversion score. But is that sufficient for our use case? Because with the same introversion or extraversion score, there may be thousands of different people who are similar or maybe dissimilar to me. So in that case, we need to expand those features. We need to include more features, and that is where the concept of embeddings comes into the picture. So let's say in this next example, we are increasing the number of features from 1 to 2. And in this case, we are taking two different features. So there will be two different values associated with it. So suppose, for an instance, the author has taken two different values as minus zero point 0.4 and zero point 0.8, right? Now, if he wants to compare between two persons with this on basis of the same different characteristics, he will be analyzing them based on those two scores which they generate. For person one, the score is minus zero point 0.3 and zero point 0.2 that you see over here. And for person two, that is minus zero point 0.5 and minus zero point 0.4. Now, based on these two scores, how can we say that J is similar to person one or person two? Now, in this condition, it is very important to mention that in the space of word vectors, in the concept of algebra, we see that there is a cosine distance similarity. Now, when we measure the cosine distances of any two different vectors, the less the cosine distance, the more similar that is. And the cosine distance similarity is also an important metric of finding the similarity between the vectors. And we find that vectors which are along the similar direction, similar lengths, are more likely to be similar semantically. So keeping that in mind, we can compute the semantic similarity by using the cosine similarity of these individual features that we have. And we find that a person one has a cosine similarity with J of around 0.87, whereas person two has a negative cosine similarity score that is minus 0.20. So person one is more similar to J, as we can see by this. And this is where we have determined that word embeddings are very much important, and this is where the concept of cosine similarity in word vector space comes into the picture. So if we were to increase the number of features from 2 to, let's say, 5 or 6, automatically the vectors would increase in dimensions. And to configure or to find out similarity between different people based on these features, we have to compute the cosine distances between all of them. And so let's say in this particular example, the cosine similarity between J and person one taking 5 different features is 0.66, whereas between J and person two is minus 0.37. So the end of this section, there are two different ideas and two central ideas. The first idea is anything can be represented in the terms of vectors. All the features can be represented as vectors, which are effectively numbers or decimal values or floating point numbers. And the second thing is that we can calculate how similar the vectors are, what is the distance between them, and to what extent they are dissimilar to each other based on the cosine similarity score that we have. Now, if we move forward to word embeddings, we can see that we will be entering a new concept where we are going to analyze the features of a particular word. Now, Word2vec, the traditional algorithm, is trained on a billion Wikipedia corpuses. And and if we are taking it, and similarly, GloVe is another different model, which is also trained on a larger corpus. So if we are going to analyze the word embeddings for the word king, as is mentioned over here, we can see this float array of different values, some positive, some negative. Now, if we were to represent it in a presentable manner by plotting some diagrams and some colors on it, we can see that a typical representation looks like this. This is the representation of a GloVe embedding of the word king. Now, why this is important? Because we may not be able to perceive by numbers how similar two vectors are, but by colors, we are easily able to perceive what is the degree of similarity between two different words, or two different, or the degree of dissimilarity between two or three different words. So in this case, in this example, if we see that king, man, and woman are three different words, and we can see this color contrast of each of these different words. Now, if we observe very closely, we can see that the color changes of the man are very much similar with the color patterns observed in the woman. These two words are hence very semantically similar as compared with king. So man is closer to woman, and the vector for man is closer to the vector for woman as compared to king. And this is represented this is represented if we are analyzing different words. So in this case, if we see this cluster of words like water, queen, king, man, boy, and if we analyze these colors, we will see that some colors remain almost constant, like this red hue over here is almost constant, and this blue hue over here is almost constant. These signify certain characteristics which are almost similar to all of them. But if we were to observe queen and king, this first row and this row over here, the king, we can see that the color contrast is not much. The difference is not much, which implies that they both may have a sense of royalty. But it is for us, it is easier to imagine royalty because they are similar in context. But for a machine, all these are translated into decimals, so, or float arrays. So you can, with the help of this only, we can convert these words into word vectors. A few things to point out is that, as I mentioned, that there is a straight rate column through different words. They are similar because there may be some features which are common to all of them. And also we see that woman and girl are similar to each other in lots of different places, which also implies that they are semantically similar. Now, if we have boy and girl, they are also similar, but different from a woman or a man. So this can be a cause of ambiguity, and you may think that how can this happen? Because boy and girl also have places where they are similar to each other, but they are not that much similar. You know, as we compare woman and man. And the last few important things are there are clear places where king and queen are similar to each other and distinct from all others. So that is what I was trying to imply, that whether there has been a sense of royalty being implied in these words, in the embeddings of these words. Now, if we move forward, we can see that just like we mentioned, we can also plot these embeddings or vector space embeddings into multidimensional vector spaces. Now, plotting these helps us to understand and visualize them clearly, and we can compute the resultant vectors of each of these vectors with the help of simple algebra, vector algebra. So, if we were to formulate a famous example, which is given by king minus man plus woman, we would be left with something which is similar to almost similar to queen. Why this is? Because king will have a different vector space, a different set of array values, particularly decimals. Man will have another array of decimals. Woman will have another array of decimals. So all these three different vectors that we see, this will be a kind of a numeric or an additive form of adding these different vectors to get a resultant vector. So in the example given over here, we can see the color contrasts of each of these. So king has a color contrast like this, which represents the king vector. Man has this man vector color contrast, and woman has this woman vector color contrast. Now, if I were to subtract man from king, we can see an intermediate layer of color contrast where the colors are not matching or are not in phase. And if you were to add queen with it, or I mean woman with it, we can see that the woman would get superposed on these colors. And the resultant that we see over here is king minus man plus woman with all the superposed and removed, colors. We can see the resultant as this color slot over here. Now, if we were to compare this equation, that king minus man plus woman, this final vector space with the word queen, with the vector space of word queen, we see that most of them have the same pattern. Some of the hues are a bit darker, and some of them are a bit lighter, but in most of the cases, the pattern is almost the same. Thus, we can say a very important conclusion in this sense is that vector algebra and the laws of vector algebra, particularly a vector addition and vector subtraction, becomes equally important in this current context, where when we are determining semantic inference or semantic meaning between the different words. And this is how the word embeddings are used. Now, the next concept is about language modeling. Language modeling is very, very important in the sense because whenever we are typing using the keyboard, we want autocorrect or auto type features. This is a very important feature to have, and the concept behind this is next sentence prediction, popularly known as NSP in NLP. So NSP means that given two or three different words, I want to predict what the next word is going to be. And this is particularly what a language model does. It takes two or three words and tries to predict what follows them. In this example that you see, we have input feature 1, which is this word thou. We have input feature 2, which is shalt. And what will be the output label? Now, based on the different trained and the pre-trained word vectors that we see, the word having the highest probability value gets predicted as the output. Now, how does this happen? Now, if we, for a time being, if we consider a traditional trained or a pre-trained language model as a black box, we can have the input features like thou and shalt, and we can have the predicted output, which is not. This is actually inferred from the trained corpus, right? But in practice, the model does not output only one word. It outputs rather a score of or a probability score for all the different words that are present in the pre-trained model's vocabulary. Now, this can be a very large vocabulary because word2vec, glove, and all these kinds of embeddings are trained on thousands of different words, preferably, arguably Wikipedia and millions of contexts. So in that case, we can have different we can have different features. So when we are considering this fact, the most important thing is having a probabilistic output for all the different words. The keyboard application knows when which one to pick, which word to pick based upon this probability scores. The ones with the highest scores get picked up. If we see the figure below, we can see that this trained language model gets redirected to the output prediction, where there is a list of different probability values referring to all the words in the model vocabulary. And after being trained, the early language models, which was discovered by Bengio, would calculate the prediction in 3 different steps, which are very, very important. So the first step is lookup embeddings. The second step is calculating the predictions. And the third step is project to the output vocabulary. The third step is very, very important and is very memory intensive and computationally intensive. So we will be looking at this towards the end, where there are special features available on it, right? Now, moving forward, the first step is discussing about embeddings, the most important part, which we are discussing now. During the prediction, we use a lookup embedding table or a lookup embedding matrix, where we have, in this example that we see, we have an embedding matrix created with all the words in the vocabulary, from aardvark, containing shalt, thou, and also incoherent words like zy, zy, zzzy, va. And there are millions of words in this vocabulary or the embedding matrix that we see. Now, if we were to find or use this lookup embeddings, we would be returned with a prediction value or a prediction probability score. And we would be able to extract the most meaningful or the most matching word by taking the maximum value from these predictions. Now, how do we train this language model? Now, as a very famous quotation by J.R. Frith is, "You shall know a word by the company it keeps," which is very, very relevant for the next topic that we're going to look into. In this context, there are some important things. When we are trying to train a language model, there will be lots of text. The input features are going to be enormous, because we are going to train it on all Wikipedia articles, all news corpuses. The second important factor is we are going to use a sliding window logic, where we are going to select a window size. The window size is very, very important for selecting 2 or 3 or 5 different words at a time. And we analyze with the help of the lookup embedding that we saw earlier, what prediction values or what probability values that we are getting with those sliding window values, sliding window words. And the sliding window is a very important model because it generates training samples for our model. And we'll be seeing that just now. Now, if we take this example, "Thou shalt not make a machine in the likeness of a human mind." This is a quotation by Dune. Now, when we start, the sliding window is on, if we take a window size of 3, the window is on the first 3 words of the sentence. That implies thou shalt and not. Now, in the data set that gets formed, we can have 2 inputs, that is input 1 and input 2, and a corresponding output label. So if we were to order or progress like this, that we take the first 2 words in a particular window as our input 1 and input 2, we want to predict the score of the output word, that is the third word. Now, if we were to go following this logic, we can say that thou and shalt, as colored by green, they are input 1 and input 2 features respectively, whereas not is an output feature, right? Now, we have generated the first sample of the data set. Now, if we progress along this similar logic, we will be generating a huge and a very big data set of window size 3, where we take the first 2 words of the window size as our input features, and the last word, that is the third word, as our output. Now, a larger data set can be like this, where we have thou shalt not make a machine in the, and if we take up till this, we can see that make a machine. If we take the last example, that is a machine in, a machine becomes input 1 and input 2, whereas the output becomes in. Now, language models in practice, they are trained by the sliding window technique. Now, there have been several advancements by using neural networks and various complex models, but there is another class of models which are called n-gram models, and these n-gram models rely on these kinds of sliding window techniques for creating a CBOW and skipgram that we're going to look into. Now, these are very extensively used, and there is a blog from SwiftKey that you can find in the link that is provided here. on how the Android keyboard uses this engrams logic to create their own beautiful data set comprising of sliding window. Now, if we move forward, we can see that there was one of the important features is that, as Jay has mentioned, that Jay was hit by a blank. Now, in this blank, we have to predict a certain word. Now, given the context, if we are given the context that J was hit by a bus, we might have guessed that J was hit by a bus. In the blank, the word bus would have been there. But suppose if there was another blank in front of the word bus, then that would change the semantics of the sentence entirely. And that would indeed change the resultant outcome that is going to be predicted by the lookup embedding. Now, in this case, if we are given by any adverb or any adjective, right? So let's say red bus in this case, then red would have been the correct answer. But what would have been like if we were not aware of this, if another blank was given? So it turns out that accounting for both the directions, that is words to the left and also the words to the right, leads to the better word embeddings. And this is quite true from an intuitive level, because if I were to just consider the words which are just forward of me, I would not be able to retain the information for the words which I have observed previously. So that is why it is always important, and all the language models use this concept that there should be a bidirectional approach where we have a look ahead and a look back, where we are using the words and the statistics, the semantics of the sentence from both forward and in the backward direction. That is where an important concept of skipgram comes into the picture. Now, instead of looking just two words before the target word, we can also look at two words after it. So this is another very important feature. So if we were to just say that J was hit by a blank, and then we have bus, and we have a continuation of a different sentence, then by probability value, from a range of probability values, we can get that the answer is red, given the word red is in the vocabulary. Now, the data set we are virtually building up by the model that we saw, that is the ngram model, it would look very similar to the example shown here, where we have input 1 as bi, input 2 as a, input 3 as bus, input 4 as in, and the output as red. Because, as we have mentioned, we are just looking two words before the target word. So we can also look for two words after it. This would not only improve the model, as mentioned before, it would also help to create better embeddings. Now, this particular thing is called as continuous bag of words model, and this was described in one of the first Word2vec papers by Mikolov, and this architecture is shown to provide great results. Now, instead of guessing a word, right, just the word by guessing the context just before it and after it, this architecture actually uses a very different concept by predicting a set of different words or phrases when we are given a particular phrase or a particular word. Now, if we get this example, J was hit, and we leave a blank after that, then by a red bus, this particular phrase will get the highest probability, or will be the result of having the highest probability value. Now, this is the CBOW model, where we are given a set of words or a set of words or a given or a single word, right? And we are made to predict what the context of it. That means the resultant probabilistic contextual vectors, right? So in this case, J was hit and we leave a blank. So by a red bus in, this becomes our context vector. So this becomes the CBOW result, right? Now, this is very, this is a very reversal of the skipgram model, where we are given a context and we are going to predict a single word. CBOW model actually tries to predict a context, that is a phrase or a group of words given a particular word or a phrase. Now, how is this created is very important, because it is one of the most important concepts here. So if you see this example, by a red bus in, so if we have the input vector as red, so the output can be all these values, right? So first we have by, then we have a, then we have red again. Red will not be taken because red we are taking as the input. So the next word comes in, bus, and the last word is in. So, and we go to the lookup embedding table, right? And we see the probability values, and we find the maximum probability value from them. So this is how the CBOW gets calculated. So we are using a sliding window concept, right? So the sliding window gets translated at each step by window size, right? We are taking some input features. In this case, we are taking just the input feature that is a single word, and we are trying to predict the context from it. That is, we are trying to look up the embedding matrix, right, for a fixed window size, and then we are finding the maximum valued probabilistic value output from that particular sample. So this is called as the continuous bag of words model, that is the CBOW model. And now, if we were to move back to your previous, predicting a single word given a particular context, we would go back to the skip-gram architecture. The skip-gram architecture is very important for predicting a single word given a particular context. In this example, thou shall not make a machine in the likeness of a human mind. So if I were to, have an input word in this example that we see over here, that is not, where not is taken as the input word, then the target words can be thou shalt make a. So these words in this vicinity, for this particular window range, this will have very high probabilistic values. And from them, when we slide our window to the next position, then we see that the next word which gets created is make. That is the input word which should be, rather than not. So because we are taking the median position in this example, we are taking the median position as the input word. So with make, we have different words like shalt, not, a, machine. So we have different target words. So if we move forward like this is the combined example. So in the first case, we have the example with not as our central input word and all the words of the window target words, right? And in the next case, we have the input word as make, as I mentioned, and we have the surrounding or the other words in the window as our target words. Now, if we were to translate this sliding window one step at a time, or depending upon the window stripe, that is how much the window size is, then we would be able to generate a big corpus, right? A big corpus where we have particularly a data set where we have a particular input word and we have the target words associated with it. So these target words are ranked based on the probabilistic values associated with the lookup embedding table. Now, if we were to, this is this entire thing, right? Creating the data set from the sliding window concept. This falls under the training the language model. Now, if we were to have our this sliding window based skip-gram model, and if we were to train it, then we were to have an untrained model, right? And we were to predict the next neighboring word or the neighboring words, right? Now, this is our data set, and we can predict our neighboring words. Now, we first start with the first sample of our data set, right? The first word is not, as we see over here in this example, the input word is not. And in its vicinity, there are different words, right? There is thou, shall, make, right? There are 4 different words in its vicinity of window size 4, of window size 5. If we take not as one of the words, that means the rest of the words are 4 in number. So from now, the next step is the lookup embeddings that I mentioned. We look up the embeddings to generate the different probabilistic values that we have, right? And we select the maximum of those values. So in this way, for not, we can just predict the next word, that is using the skip-gram, skip-gram sliding window model. The next thing is calculating the prediction, right? And the prediction is calculated by taking the maximum probabilistic value. Now, this prediction is then, initially when we train a language model, or when we are doing a training based on a supervised task, right, there is always prone to be an error which gets computed in the initial stages. Now, this error is due to many things. This can be due to not incorrect parameters, incorrect output, right, incorrect weights. And in supervised learning, we this learning is moderated with the help of weight updates, right, weight update rules. And in this case, the weights are nothing but the prediction vectors and the error vectors, right? So in this case, we have an actual target vector of, in this case, we see on the left as 0, 0, and 1s, that is binary, right? Now, why binary is very important, I will come to that later. But if we just consider in this example, the original one, that is the probabilistic values, in many cases, we see that we may get different probabilistic values during the initial training stages. Now, there is bound to be some error in the training. So we have to mitigate this error. So how do we mitigate this error? We get the prediction vector, right? And we subtract it from the actual vector that we have. Now, very similar to this. Now, this is the actual target vector. Imagine this as 0s and 1s for now, just for simplicity, right? And this is the model predicted vector. Now, when we subtract the actual target vector from the model vector, right, predicted vector, we get the error vector. Now, this is the weight that is getting that is analyzed as the weights in the supervised learning model. Now, the language model gets trained like this. They get the error vectors and they updates the weights or particularly the vectors of each of these words, right? And this is how the training goes on iteratively for epochs and epochs until we get a proper balanced, predicted vector with the actual vector. Now, the importance of this actual target vector being in binary is because the logistic function has a very simplistic, being in binary has a very simple application in the sense that it is computationally very fast because there are only two labels, right? Zeros and ones. So there are no intermediate values. Either it is correct or it is wrong. And this increases the speed and or the efficiency of any machine learning task that we see. So that is why it is best kept to have these things in as a logistic function or as a binary function, right? So all in all, we have seen how we can train a language model using the sliding window concept, that is skipgram. We have also seen how CBOW is used to find contextual words given a particular set of words. We have seen how we can use the lookup embedding table for each individual words in the skipgram sliding window to get the most probable or the word with the highest probability as the next predicted word. So this is the concept of next sentence prediction on NSP, where we are trying to predict the most probable word by analyzing them in windows, sliding windows, looking up the embedding table, getting the maximum probability value, and then training a neural network model in a supervised manner, right? Where we have error vectors, prediction vectors, try to rectifying the prediction vectors so that they correspond with the actual vectors and so on. Now, there is another important concept in the paper of Word2vec is that negative sampling. Now, negative sampling, as I mentioned in my previous case, that there are three different steps. The first is the lookup embeddings. The second is the calculating the prediction, and the third step is outputting the prediction project to output vocabulary. Now, this is very computationally intensive, and this is because when we are outputting the vocabulary to a large set, there is a computation time during inference as well as converting those probabilities to individual words. Now, there are two different ways to split it, right? The first is generating high quality word embeddings. This is very good feature to have. And then the next step is to use these high quality embeddings, right? And then train a language model again. So instead of having to train these kinds of language models and project to the output vocabulary, we can already create high quality word embeddings, and then we are going to see the importance of this binary function, that is 0 and 1 function, that is a sigmoid function, and why it is very computationally faster. So if initially we had this concept where we are going to have an input vector that is an input word that is not, and we are having an untrained model, and we are predicting the next word that is the NSP or the neighboring word that is thou. Now, if I were to just convert this to a slightly different value, right? In this case, I will be getting a value of 0 and 1 for wrong answer and right answer respectively. So let's say we switch it to a model, right, that takes the input and the output word, and we are trying to predict whether it is correct or not. So let's say if I'm taking the input vector as not, as in the previous case, and I take the output vector as thou. Now I pass it through the model, and I want to see that whether the not, that is the input vector, is thou or not, right? That means after not, thou comes or not. So this can be thought of as, this is very confusing example. So let me give you a different example. So in place of not, let's say mask. Okay. So let's say what is the probability, right, that the word thou comes after the word mask? So if it is 0.9, that means that it is correct. That means it is correct, that we have taken our assumption as correct. Now, if it is very low, that is, let's say 0.5 or 0.1, that means we are wrong. We are wrong in our assumption that thou does not come after the word mask. Now, this concept is very computationally faster, because instead of trying to generate probabilities between 0 to 1, we can clamp them as either 0 or 1, that is binary logics, right? And this is very this speeds up the model performance to a lot. And this is where we convert this neural network model to a basic logistic regression model, and thus it becomes very fast and easier to calculate these different probabilistic values. So in this example that you see, in the example make, So make, shalt, make not, make a, all these have initially 1, because when we're training it at the for the first time, all of these words will be in the vocabulary in its surrounding words, because we have taken a sliding window size of 5, and we have taken, as we recollect in the example that we took, make was in the middle, and there were 2 words on either side of it. So all these words, that is shalt, not, a, machine, all of them come in the context of neighboring words, right? Also initially all of them will be 1. But how can we make, how can we for if we include all these ones, it will be very redundant and a waste of time, because as Jay mentioned, it will be a smart ass model, because it is always returning 1. And because if you take a sliding window, all of the words in the sliding window for a particular word will be its neighbors. So if we take make as an example over here, then shalt, not, a, machine, all are in its neighbors, so all will be 1 by this logic. So how can we improve this efficiency? How can we improve this logic? So the next step came in is negative sampling, where we take totally different words, totally different phrases, right? Phrases which are from different windows, right? So let's say the first window was in paragraph 1 and the second window was in paragraph 2. So these are far apart. These windows are far apart, and we are trying to create a different data set from this where there is noise. That means if I place a word which is in paragraph 1 with respect to paragraph 2, it is not there in its context, so it is not there in its neighboring words. So in that case it becomes a 0. This is called as negative sampling. Now, by negative sampling, we mean that we are taking different word samples or different phrases from different parts of the text, right? In this example that we see that not here, we can take a different output word. We can either leave it at blank, or we can take a different output word. Let's say aardvark. So not an aardvark, they are not related in by any chance in any corpus, right? So in that case, it becomes a negative sample. So this negative sample is used to create zeros for our models, right? For our data sets, for our target values. And this becomes a classic logistic regression model. So in this case, just to summarize, we have taken an input word that is a not, right? Our task is to alleviate or remove this project to output vocabulary, this computationally intensive task, by generating very high quality embeddings. For this, we convert our model to a logistic regression model where we have either a yes or no answer, whether this word is the NSP or the neighboring word of that input vector or not, right? To do this, we first create the samples, right? We first create the samples, and in the initial stages, since all the words in a particular sliding window will be in its neighbors, so all of them will have initial value of 1. Now, if we move forward, we can create negative samples by taking extracts from different parts of the corpus, right? Now, this will allow us to have a very diverse and a 0-1 based corpus, which is suitable for logistic regression and sigmoid classification. And that is what is exactly done. In this example that you see, not and Aaron are not at all in the same corpus and are not at all in the same semantics as the data set, right? So that is why they have a target value of 0. And this is a negative sample. Again, not and taco, these are also negative samples, and that is why it is a target value of 0. Now, with this data set, we can classify it in a binary manner. And this is called as noise contrastive estimation. Now, this is a very important part of the paper which was proposed during Word2vec, and it is highly recommended to take a look. This is how what we have talked about, from using our sliding window concept for scriptgram, right? And then we are generating the lookup table, and we're generating the embeddings, right? And we are then converting them to high quality embeddings by making the model a logistic regression model, right? By making the model answer yes no questions, right, based on probability values. And then we are creating negative sampling just to add zeros to our data set to make the data set more diverse and properly suitable for logistic regression. And this entire concept is called a skipgram with negative sampling, which is abbreviated as SGNS, right? And this is a very important concept, and this has improved the performance and efficiency of the Word2vec model. Now, the training process of how Word2vec was trained is very simple. We have 2 different matrices. One is the embedding matrix and one is the context matrix. Embedding matrix has all the embeddings of the words that you see, and context matrix is another matrix which is almost similar to the embedding matrix but has the contextual words for a particular word. Now, embedding matrix, as it is mentioned, 300 is common size for embedding matrix, but we can create any size. And also we can have a vocabulary size for creating these embeddings as we want. Like in this case, we have 10,000, but it can be anything. and we are using this the model that we saw earlier, that is the negative sampling skipgram based model of logistic regression, right? And then the next thing is a procedure of how training is done on this logistic regression model, this logistic regression data set. So the embedding matrix and the context matrix, right, we are used by the lookup embeddings, right? And then they're used to generate whether not has the word Aaron, taco, or thou, which of these three words as the next word. So as it is mentioned, so let's say we have four words, right? The input word is not, and the output contextual words are thou, Aaron, and taco, where Aaron and taco are the negative samples that we saw. Now we proceed to look up their embeddings, that is the embedding table, right? For the input word, we look in the embedding matrix. For the context words, we look in the context matrix, right? Even though both the matrices have an embedding for every word in the vocabulary, they are effectively the same. But what we are using the embedding matrix, and we are using the context matrix to look if they are, matching. To look if they are matching, that means we are having a mapping from one embedding matrix to the other embedding matrix. This is how the word2vec was trained, and by this we can identify that Aaron and taco are negative samples. Now the next step is to take a dot product of this. The dot product is with the input embedding vector that we have and the context embedding vector. So in this example, we are taking a dot product of the word not with the word thou, and the target value is 1. So input dot output becomes 0.2. Now not with Aaron has a target value of 0 because Aaron is a negative sampling, and it has a value of minus 1.11. And not again with taco has a value of 0.74. So in this way, we take the dot products to get their values. Now, a very important function is sigmoid function. Now, we can translate this function into a binary or a logistic regression function by converting these, by passing this to the sigmoid kernel or the sigmoid activation, right? When we pass this input dot output to the sigmoid function, we get these translated values. So for 1, we get 0.55, that is for not and thou taken together, dot product, right? Not and Aaron dot producted gives 0.25 as our sigmoid score, and not and taco gives 0.68. Now, why we do this? Because we need to normalize the scores between zeros and ones. That is why we need the sigmoid, right? And we can again compute these errors, right? As we mentioned in our training stage, right? We have the predicted vectors and we have the actual vectors, right? The predicted vectors that we see over here, the target vectors are actually 1, 0, and 0. But the sigmoid, this gives the predicted vectors. So we compute the differences between the target vectors and the predicted vectors. So it is 1 minus 0.55, that is 0.45. Right. So 0 minus 0.25, it is minus 0.25. So this is the error vector that gets generated now, which is effectively the error weights. We can see over here that error is equal to target minus sigmoid scores. The next part is the learning part, where we update these weights, where we update these vectors, right? And this is how in the pictorially this model weights are getting updated. This concludes the model training step. So we have seen how the model gets trained. The main important concept is that we are converting the model into a yes-no logistic type of regression model, where we are trying to generate, where we are trying to give a word and a corresponding output word, and we are trying to say whether this word is the neighboring word of that. So this becomes an effective logistic regression model. Then we use negative sampling to generate zeros or for our target labels, right? So that we can have negative sampling. And then we have seen how we can use the word2vec, how we can train the word2vec by using this negative sampling skipgram technique, right? And we have seen the entire process of how we take the dot products of these two vectors, that is the context vector as well as the embedding vector, right? And we take we have the target vector associated with them, right? We take the dot product, we convert them to a sigmoid function to scale it between 0 and 1, and we compute the error vector, that is the target vector minus the error vector. So because we have a supervised learning thing that is going on, so as discussed earlier, right? So this is how the model training and the word2vec model training is done. So this model training is effectively a skipgram, a sliding window based embedding model, right, which is trained on logistic regression. Now there are certain hyperparameters like window size and the number of negative samples that you want to take. Now, the two key hyperparameters in the word2vec training process are the window size. In our case, we have taken a window size of 5 in our example, that is thou shall not example, which Jay mentioned, right? Now, different tasks have different window sizes. One heuristic is that smaller window sizes, that is range between 2 and 15, lead to embeddings, where high similarity scores between two embeddings indicates that the words are interchangeable. That means that antonyms are often interchangeable, and and if we are looking at the surrounding words, that is good and bad, often appear in the similar context. So what does that mean? This means that if you're taking very high or very large, if you're taking very small window sizes, that is between 2 to 15, these embeddings have very high similarity scores, because there are chances that these words can be used interchangeably in the corpus. Now, if we have a larger window size that is greater than equal to 15 or more than 15, then the similarity is a more indicativeness of the relation between the words. That is how semantically related a word is to another word, right? Now, for a particular, as a notification, the GenSim window defaults window size is 5, 2 words before and 2 words after. Thus, it's the same as we mentioned in our, thou shall not example that we see over here. So, and there are negative samples associated with it too, right? So if we see over here in the negative samples how it is used in GenSim, right? We take an input word make, we compute an output word shalt, right? It has a target value of 1 because shalt is in the neighborhood of make in the slide in the same window, right? Make and Aaron is not in the same window as make, so it has a value of 0. That is, it is a negative sample, right? So similarly, these samples are getting generated. So that was entirely all of the different things that was taken, different concepts from Word2vec embeddings, right? So effectively, what we see, to summarize, the most important features are that if we just move back, we have taken some important key points, that cosine distance is one of the most important features, right? And to represent any feature or any particular entity, be it a word or be it a sentence or be it any real world entity, we need vectors, right? We need properties or features, and we can calculate the similarity between features by taking cosine distances or cosine similarity. When we come to word embeddings, we have seen how different words and their embeddings are generated, right? As a tuple or an array of decimals, how we compute the similarity between different words by using the additive vector algebra that we saw over here, king minus man plus woman equal to queen, right? We also saw about NSP, that is next sentence prediction in language modeling, how we initially created a black box model and we tried to predict the output word, right, given a particular word. And we saw how this utilizes a lookup table or a lookup embedding table to find probability values for each and individual words in the particular corpus, in the particular vocabulary, and gets the maximum probabilistic value as the output. We also saw how to train a language model, right? First, we analyzed it using the sliding window, right, which is a very important concept. Inside that, we had taken an example of skipgram, right? We had taken an example of skipgram. First, we had created a data set where we are taking, in this case, we are taking a data set size of 3, right? Window size of 3 to create our data set, where the first 2 words are the input features and the third word is the output feature, right? In the next example, we have taken, got to know about the feature of skipgram, where we try to predict a word given a particular context, as in the example mentioned by Jay, was hit by blank and the blank bus comes in, right? Then we have continuous back of words model, where we have a particular a word or particular phrases, and we try to predict the context or the next phrases, common phrases in the words, in the vocabulary or in the sentence, right? So Jay was hit, and if we leave a blank, by a red bus gets predicted. So this is a continuous back of words model, right? We also saw how to train these samples, right? How in this example, we have used a skipgram window size of 5. We have taken the middle word as our input word, and the rest of the words in its neighboring words are the target words, right? And and we create the data set like this. Now, for training process, we already mentioned training process. We have the input words and the target word associated with it. Now, in most of the cases, there are three different important features: is lookup table, calculate the prediction, and project to the output vocabulary. Now, projecting to the output vocabulary is very computationally intensive, and the training process constitutes having an actual vector and a predicted vector, and computing the differences or the error vector from them, and updating those vectors repeatedly. Right. This is what is mentioned in this blog. And then we have the negative sampling, because we want to increase the efficiency by alleviating this project to output vocabulary part. So we are creating very high quality embeddings, and we are changing our model to a logistic regression model, right, where we ask only yes and no questions. That means whether whether thou comes after not. If it is true, then it is, in this case, it is 0.9. That means it is true. And if it is false, it is close to 0, right? So in this case, initially we will be having all the scores as 1, all the target values as 1, because needless to say, all the words in a particular vocabulary in the same window are in its neighbors. Now we have to create negative samples for our training data set. Negative samples are created by taking different phrases from different parts of the text, which are not at all related. So we go down and we see that not and Aaron are not related, so they have a negative sample of 0, right? Negative target of 0. Not and Taco are also not related, so it becomes a negative sample again. So what we have seen up till now is a skipgram with negative sampling. And when we try to train this Word2vec model, we are using two different math tables, that is embedding table and a context table, right? Both these tables are used for looking up, right? So if we see not and thou, right, they have a target value of 1. Not and Aaron, they have a target value of 0. So that is a negative sample. So first we create, we take a word from the input word, right? And we try to say that the output word is thou from the context, right? And we have a target value of 1, right? Because it is thou is there in the window. But we also compute the input dot output, that is the dot product of these, right? And after that, we translate them to the sigmoid function, because we want to clamp it between 0 and 1. And after that, we compute the errors. Just like I mentioned before, we compute the errors by subtracting from the target vectors the sigmoid vectors, right? And then we update those vectors, right? And this is how the supervised training model of the logistic regression takes place by skipgram, noise contrastive estimation on skipgram, skipgram with window size, right? So in this context, we have learned a lot about negative sampling, how negative sampling has improved the accuracy by converting the model to an entirely new model by improving the efficiency of the model. This negative sampling has only allowed us to train on large corpuses in a very moderate amount of time, because instead of training it on and using probabilistic values for all the different words, we are trying to have an yes no based answering question, where we can have a logistic or a sigmoid kernel or a logistic function to classify it for us using negative sampling. Now there are certain hyperparameters like numbers and negative samplings, how much negative sampling we want to use, what is the window size and numbers. Some heuristics are mentioned in this, and these are all some of the important features that I wanted to mention. And definitely this blog is very good for reading different other articles on it. That is all that I had to cover, and I hope to see you guys in the next video tutorial. Thank you.